Okay, welcome back everybody. I hope you had a restful break between my last video and this video. I was hoping that this one would come out a little bit earlier, but it took me a little bit longer to focus on learning the material because I had some school stuff that I was also doing, but that's just an excuse. I should have gotten this out a little bit earlier, but that's beside the point. I'm glad to be here right now doing this. So what are we going to be talking about today? Backpropagation. So cool. But yeah, it's basically the lower level of how networks learn. So we're going to just be learning a little bit about that. I'll give you a brief, I'll give you like a somewhat, like a little, it's deeper than a shallow level explanation, but not as deep as other videos have gone. But yeah, if you're interested in learning about this in more detail, I will provide links to the resources that I use to learn about this. There are a few really good videos by the YouTube channel 3 Blue 1 Brown, and there's also the online book that I've been using to just learn about machine learning in general, and that goes into great depth into the calculus and whatnot of all this. So if you're interested, I recommend checking those out. I will put links in the description below if you are. But yeah, with that, let's get started. There will be a little bit of math. I won't go into a lot of detail about the math, so don't worry. This is just kind of an overview of backpropagation and just to provide a little bit more context into my current understanding of machine learning. Just another building block in the steps to learning about it. So with that, let's get into it. So the first reasonable question to ask as a follow-up to my previous video, which was about, the architecture. Well, the previous video was about the architecture of networks and whatnot, but what is a network if it can't learn, right? So the next logical question is to ask, okay, well, how does a network learn? How can you make something that's purely theoretical or on my computer in some code, in some memory addresses, whatnot? How can I make something actually learn? And it turns out it takes a lot of math, more math than I would have thought, but I'm glad that my school makes me take certain math courses because it makes more sense than it would if I didn't take those. So there's a little bit of multivariable calculus involved, a little bit of linear algebra, which I won't be covering, and some statistics, which I also won't be covering, because frankly I don't want to. But you can check out the more in-depth videos that I mentioned earlier, and they'll do everything you would ever want to know math-wise. But yeah, so it turns out that these machines learn through algorithms, which we'll get into a little bit more, but a good way to kind of visualize networks is I just have a small little example here. So we have two inputs and our output, and these are the neurons and the links between them, whatnot, But yeah, so like we previously mentioned in the architecture video, is that each neuron has a bias associated with it, and also the connections between neurons have weights associated with them. And we can kind of think of each of those elements as a sort of dial that can be changed to be either greater or lesser than its previous value. And essentially, as a really large simplification of the process, what the machine does to learn is it figures out how it needs to adjust each and every one of those dials to get the desired output, or to get an output that is as close as possible to the desired output. And so we'll talk a little bit more about how we can kind of measure whether the machine produces an output that's close or not to the actual value. For a specific type of learning, but that's aside from the point. But kind of like I mentioned last time, when we initialize our network, we're basically setting the weights and biases, to random positions, at least at this point. I know there are methods we're going to be learning about and talking about soon that allow us to not randomly set those, because it turns out if you randomly set the weights and biases, you can actually slow down learning and whatnot, and it's just overall not a great idea in the long term when we do more advanced stuff later on. But for now, we're just going to consider that we initialize our network to have random weights and biases, And even though that's not ideal, it's just a good starting point. But yeah, so basically, through the math involved in the learning process, over many training examples, like you saw in the video where I was running the network on my computer, it was running through like 50,000 training images and then 10,000 testing images, and it does that whole thing like 30 times, depending on what you set the epoch number to in the hyperparameter, whatever. But yeah, so the learning process is just basically figuring out how we need to turn these dials or adjust the weights and biases to get outputs that are as close as possible to the expected result. At least for this particular example that we're kind of focusing on is comparison, or what is it called? Comparison neural network. Comparative, something like that, where it's it's comparing a result that's been given to something that is produced. So in this case, we're producing a digit that we think the identity of the handwritten digit is, and then we're comparing that to the tag or the label, because this is supervised learning. But yeah, basically, that was a really long-winded way of saying that machines learn, at least through this particular method, by figuring out what they need to do to each and every one of these weights and biases in order to maximize the accuracy of the network. And that happens to involve calculus. And so I'll just provide a little bit of context to this calculus approach that we're going to be talking about. Now, there's going to be two main concepts that we're going to be talking about, backpropagation and gradient descent. We talked a little bit about a gradient descent, I think, maybe in one of the last two videos. I can't exactly remember, but regardless, we'll talk about it here. So just a little bit of context if you haven't taken multivariable calculus at all. There's this concept of a gradient, and typically it's used for multivariable functions, which in this case, that's what we're dealing with. Well, I haven't explained that that's what we're dealing with, but in a few minutes you will know that that's what we're dealing with. And the gradient is essentially a vector containing the partial derivatives of a function with respect to each of its multiple variables. So if there's a function like this, for example, that is dependent on x and y, then the gradient would be a vector containing the partial derivative of f with respect to y and of f with respect to x. So here's just a little interpretation of that. So the gradient of some function is a vector of each of its partial derivatives. And what the gradient tells us is the direction from the direction that we need to move from where we are currently. That was a dumb way of saying it. The gradient is the direction of maximum ascent. So where we need to go to increase the function the most. And it turns out that we actually want the opposite of that. We want the direction of maximum decrease, which just happens to be the negative gradient. So not much different. So you can kind of think of the gradient, you can kind of be like, okay, it's almost like a compass where instead of north, the dial always points in the direction of steepest descent. And what we're trying to do is get all the way down to the lowest point in some function, which I will explain in a little bit. Probably should have explained it before now that I think about it. But basically, I'll give you a little bit of context. We can describe our network with a certain type of function, and the goal is to use this method for finding the gradient and using this method of gradient descent to find a position on our function or on the function's graph that minimizes the function's value. And this is going to make a lot more sense when I go to the next slide. I should have done this in a different order. But yeah, so this is all about multivariable optimization in essence. And I think we talked about this previously, but you can also include topics. So basically, let me catch my thoughts here. Yeah, so the calculus that you're going to need to know, basically, to understand my slides is like, okay, we're going to use backpropagation to find this gradient, to find the gradient of the function that I'm about to describe, and that will help us figure out the direction that we need to move to minimize the value of the function. And it turns out that we can yeah. Interesting. As you can tell, I'm obviously not the most knowledgeable about backpropagation yet. I've only been studying it for like 2-ish weeks, so cut me some slack, okay? We can learn together. Anyways, so yeah, blah, 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 blah. We're all about minimizing, okay? Minimize, blah, blah, blah. We're all about this math stuff. But how can we minimize a network? How can we represent a network in a function that we're able to, apply all these calculus concepts to? And it turns out we're going to need some sort of metric of the network's performance, and we call it the cost. The cost function is some function of the network's output, so what the network produces, and the expected result. So this is, I think, pretty much only applicable for networks that are supervised or semi-supervised, or they do semi-supervised or supervised learning, because then in those cases you'll have an expected output, whereas for other types of learning you might not. So this is kind of just a beginner's introduction to the math of networks, and that's fine. But anyways, so as an example, we could define the cost function to be, the positive difference or the squared difference between the actual and expected value. So, for example, if our network outputted, a 4 when the expected value was actually a 3, it would just be like 4 minus 3, which is 1 squared. So we have a cost of 1. And if we did that over different training examples, blah, 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 we might get different results. Now, as I was previously describing, we want to get to a point where the cost is a minimum. And so, so the cost is our function, which, like I said, is a function of the output of the network and the expected output. Now, the expected output is not something that we can change through training. The expected output is something that's given. However, the output of the network is something that we can change through adjusting these weights and biases, as I mentioned before. And so, if we use some calculus, we can figure out what those adjustments need to be. And so the actual value, so what the network outputs, is directly related to the weights and biases of each node or each neuron and connection in the network. And so this is the part that gets a little iffy, kind of, but I'll try my best to describe it. So backpropagation basically goes in reverse order through the network. So we start at, say, the output neuron, and then from there we backtrack through the network, seeing how a change to a certain weight or bias might affect the output. And so, for example, in this little example with a 4 network, so these are our outputs, here's our input, and here's our hidden layer. It's not that big of a network, but you see, if we change this weight here, then basically the input to this neuron is going to be changed, which then affects this neuron and this neuron. And so you can see the same thing if we change the bias here. It's going to change the input to this neuron, which then changes the input to this neuron and this neuron, blah, 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 blah. So basically, these changes to the weights and biases propagate through the network and cause, maybe large, maybe small changes in the cost. And so we can take these measurements, so for a single training example, if we make an adjustment to the weight, we see how it goes through. Well, we would actually do this in reverse somehow, doing some crazy stuff. That's just like a little hand wavy thing that I'm going to do, and I'm going to recommend that you watch the more in-depth videos by 3 Blue 1 Brown, or the book that I recommended if you're interested in the more detailed explanation of how this works. But yeah, so it turns out we can figure out the relative, basically we can figure out how the cost function for a particular example changes with respect to any given weight or bias. And so that's what this represents here. It's just how much does the cost change with respect to changes in a certain weight, how much does the cost change with respect to a certain change in a certain bias, blah, 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 blah. And then we can use that information to do some gradient descent. So this means adjusting our weights and biases by just some little bit to get one step closer to our desired minimum place, which is, mathematically speaking, where our network would be producing outputs that are, the best in a sense. But so we make those adjustments, we do some gradient descent, we get a little bit closer to our desired minimum, and if we continuously do that over multiple training examples, then hopefully eventually we'll reach the optimized state, which is, the state that I was mentioning before, where we're at the lowest possible point on the graph of our function, which means that we're going to be getting the best results that we can. And so that's, so we've defined the cost function. The cost function is a function of the network's output and the expected output, which the actual output is affected by the weights and biases. So we use some calculus through backpropagation to figure out how we need to change those weights and biases, and then we go back forward through the network, making our changes to the weights and biases to, follow this pattern of gradient descent until we reach our optimized state. So that's just like a pretty hand-wavy approach to explaining backpropagation on a pretty simple problem. So by no means am I here to instruct all, reinvent the wheel. That doesn't make sense. I'm not here to provide you the most detailed explanation. I'm just here to make a record of what I've learned so far. And I don't need to justify anything. Anyways, so just a quick summary. As I was kind of explaining here, there's a little bit of a cycle, right? So we have any given training input goes in, the network runs, we get the network's output, and then we, use our cost function. We compare the network's output to what's expected, and then through our backpropagation algorithm, we end up getting the gradient of the cost function, which gives us basically measures of how much each weight and bias changes the cost. So then we can go back through the network through gradient descent, updating the weights and bias, or we don't go forward through the network via gradient descent, but the process of making these changes is essentially gradient descent because we're adjusting our position on the graph closer to our optimized minimum or optimized state. But so blah, blah, blah. We get the gradient of cost function, we make the necessary adjustments to each weight and bias, and then we get another training input, network runs, blah, blah, blah. We get the output, backpropagation, and then we make our updates, and this just continues and continues and continues and continues and continues, blah, 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 through all the training data, and then we can test it. So this is like in my previous video when I ran the network, the X correct out of 10,000 was actually, after all of this training was complete, it would kind of test its results against the 10,000 pieces of testing data. But before that happened, during the time between one epoch and the next, one epoch showing up in the terminal and one in the next, it would actually be doing this cycle on 50,000 training images, which is pretty crazy. So kind of just coming back to the beginning, we started at a random state. And then over all the 50,000 training examples for, in the context of the previous example in the video, we go through our training iterations, making these changes to our weights and biases, continuously descending until we reach our minimum, and the minimum is in reference to our cost function, which again is a function of the network's output, and the expected output, which is, directly determined by the values of the weights and biases, which I said are the key to learning. So we make those adjustments through the training data, and then eventually, boom, we can reach our optimized state, hopefully. And at that point, we will be hopefully predicting everything you could ever want about handwritten digits. But this doesn't just apply to handwritten digits. There are other, algorithms that use this form of learning or some branch of it. That was pretty quick. Probably not the most detailed description of this, but yeah, anyways, this is just supposed to be a record of my own learning, so that's what this is. But yeah, if you did make it to this point, I congratulate you, because I honestly don't think that I could make it to this point. But if you're interested more in learning about the details of this, mathematically speaking, and with someone who knows a little bit more about what they're talking about, then I would recommend checking out 3 Blue 1 Brown, the videos that I will put in the description below. And also check out the book. It's free. It's great. It's a great book. But yeah. So what will be the next thing that we will be talking about? Turns out it's more about learning, because the next chapter in the book that I'm reading is all about about methods that we can use to improve on our current learning methods. So that's like what I mentioned before, with the issue of starting in a random state, is that we can actually cause the network to run extremely slowly, depending on the activation function that we're using, depending on the cost function that we're using, depending on the activation function we're using, blah, 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 blah. So yeah, there are ways that we can improve learning by, first of all, not putting ourselves in a random state to begin with. There's also improvements to figuring out how we can make adjustments to the hyperparameters, like learning rate, epoch number, sample size for stochastic gradient descent, all these things. So we're going to learn about how to improve the learning process, probably learn about some more activation functions. We'll talk in general about more about learning. But yeah, for now, I hope this was helpful for anybody, even if it was just me from the future. But yeah, that's kind of pretty much it. Wasn't the most exciting, but it needed to get done. So anyways, there probably will be another short video coming out just describing some exciting things that's coming. So with that, I will leave you to whatever it is you were doing before this. I wish you the absolute greatest day in your entire life. I hope everybody's doing well. And yeah, I'll see you next time. Let's freaking go. Do some freaking machine learning and stuff. Let's freaking go. Let's freaking go, bruh. Sorry. See ya.